This resource on differentiation looks at the origins of the product rule. So previous videos introduced differentiation from first principles, and it's logical to consider what consequences follow from this derivation. The product rule then is one of the consequences. It's a scenario where a function comprises the product of lots of other functions. So how do we find the derivative of a function which is the product of other functions? Now you're reminded, if you're not overly interested in derivations, you can go straight to the 6th resources, which starts on worked examples. Product of functions then. So what scenario are we looking at? Let's look at something like this. Y equals f of x, which is 4x squared times cos 2x. You see there's two separate functions which are multiplied together, so it's the product of two functions. Or here you have 3w to the minus 3 times sine w over 2. So g of w is the product of two other functions. And here's a final example. H equals k of t, which is the product of 0.2 t squared and e to the minus 0.1 t. So the question we've got is, how do we differentiate such functions? So what's the core result? The derivative of a product of, and you'll see I've said two functions, I'm restricting myself to two for now, is given by the following formula. If y equals u of x times v of x, so you've got function 1 u of x, function 2 v of x, then the derivative dy dx is given by u times dv dx plus v times du dx. So this is a result. Now staff often verbalize this with the following sort of shorthand. You'll see they say u dv plus v du. It's important you say the letters separately, so u dv plus v du, and that's a shorthand for saying I'm using this formula here, this product formula. So let's remind yourselves of the definition of the derivative. A limiting value, so dy dx is the limiting value as dx delta x tends to 0 of y of x plus delta x minus y of x, so the change in y divided by the change in x, or an equivalent formula with other variables if you prefer. So what we're going to do is apply that formula to our product u times v. So here's the formula, y of x plus delta x minus y of x over x plus delta x minus x, and I simply plug in uv where I had y. So you see I've now got u of x plus delta x times v of x plus delta x minus u of x times v of x. Now from the definition of derivatives, and you might need to go back to resource 2 to convince yourself of this, then what you've got is the limiting value as delta x goes to 0 of ux plus delta x is given by u of x plus delta x times du dx. And that's actually just a definition of the derivative rearranged. In a similar way, the limiting value as delta x goes to 0 of v of x plus delta x is v of x plus delta x dv dx. Now why have we done this? Because I'm going to take this formula here and put it in here, and this formula here and put it in here. So let's just reproduce those three equations, and now when I substitute in, you'll see I end up with u of x plus delta x times du dx times v of x plus delta x times dv dx. So I've slightly rearranged my definition for the derivative, and now all I need to do is multiply this out longhand. But when I do that, I'm going to ignore all terms in delta x squared, because you remember that delta x squared is much smaller than delta x as delta x goes to 0. So if we multiply this out longhand, we get this expression here, but you'll notice I've ignored the delta x terms. Now on the next slide I'm going to reproduce this equation, so I'm not going to do any simplification at this point. So here we go, I've just put this equation down again. Now if you look at this equation, you'll notice this term and this term cancel. And so what you get left with is this. dy dx is the limit as delta x goes to 0 of v of x du dx plus u of x dv dx, and then we've got two delta x terms which cancel, and so you get your result. dy dx is v of x du dx plus u of x dv dx. So now we've got a few examples to show the formula being used. Find the derivative of the following. So you'll see I've got a product of two functions. I've got an x squared and a cos. So I need to define what is u and what is v. So here I'm going to define u as x squared, so du dx is 2x. V as 4 cos 2x, so dv dx is minus 8 sine 2x. And all I do now is plug each of these values into my formula. So I just take the values and plug them in the formula. Nothing else, nothing complicated. You've derived the formula, so you just need to plug everything in. And so when I do that, I get dy dx is 8x cos 2x minus 8x squared sine 2x. If we do a second example, so we've got 3w to the minus 3 sine w2, and again my first job is to define what am I going to call u, what am I going to call v. Well, in this case I've decided u is going to be 3w to the minus 3, so I can do the derivative of that. V is going to be sine w over 2, so I can do the derivative of that. I remind myself of the product formula. There it is. And now all I do is take the values, that value there, I just plug them in to the formula. So all I do, plug the values in to the formula, and there's the answer. So in summary, this brief resource has shown that the derivative of a product requires a particular formula to get simple solutions. So what we're saying is if y is the product of two functions, u of x and v of x, then the derivative dy dx is u dv dx plus v du dx. So it's a very simple formula to remember and to use.